So, as promised, today will be a split lecture in the sense I'll finish what I started the last time on probabilistic motif finders. That's the last part, and then I'll start with phylogeny, which is very loud, I think. Better like this. Okay. Yeah. And I'll start in the second hour with phylogenetic methods. First, a little biological background, what they can entertain. Then I'll start on something very general, you should remember for the rest of your lives, because it comes in handily if you go into Albert Heijn and so on, you know, supermarkets. General points, as I promised. Also this lecture. But yes, we get there when we get there. So, first, without further ado, let's finish the last bit. I showed you a method, for example, the last time I ended up with this method called C, using multiple alignments, using the fact that with evolution, that at least there is conservation, which can be used to recognize things that are more present than you would randomly expect, which can be meaningful to know. Now we'll go also to methods that do a bit of that, but also methods that work maybe without much evolution, with the probabilistic framework. Anyway, so here you might recognize what this is. You see an alignment, say DNA alignment, 6 sequences, 6 letters each, Kepler's alignment. And you see a profile here abstracted from that alignment in its most rudimentary form. It just counts the abundances of the residues of the nucleotides in this case, summed up, abstracted in it. And so a profile contains information from multiple alignments typically. Now, how can this be used? You can, of course, easily convert each of those abundances to frequencies by dividing each number in each column by the column sum, normalization, and then you have frequencies. And if you have those frequencies, you can resort to all kinds of information theoretical things. I don't know if you've seen that on top. That is a very historical formula there, because that is Shannon information theory. This is the basic Shannon formula. Sum frequency times the log of a frequency, take the negative of that, and that is Shannon. That is information content. Now, you can do all kinds of things with that. You see that you can scale it in another way. Here, minus that, for example. Or you can go, so there are all kinds of information measures that use this basic fact, Shannon theory. For example, you might have seen this, maybe in the course of sequence logos, totally foreign to you, you've seen that, good. So if you want to know what that is, basically that formula here, sorry, let me go away. So here you see that, you know, these frequencies times the information content gives the height of the letter. The idea, of course, is the more conserved, the bigger the letter becomes. So it's intuitive. So this is in the back. If you want to check the formula, you can do it like that. Use the formula and calculate what the height for a letter in a multiple alignment would have to be. Right. So basically, almost as always, there are correction steps you might need. You know, the zero problem, we've discussed it in many guises here. Guises that works here as well. So you see also here, you have the notion of pseudo counts. You see the first one, for example, you just avoid zero numbers, which are not pleasing to most of mathematics. Okay, so basically, the point is about these simple profiles. You know, they're great. You can scan, but very often the specificity is maybe not that great. So you tend to get a lot of false positives. Things that seem to be of importance but turn out not. Okay, let's do an example. That example is by the author himself, Terry Storrow, coined greedy motif clustering. So watch it where you see the greediness coming, right? So basically, I think I could go, here's a description of what happens, but that's a bit tedious to read for you. So let's look at an example. It's much easier. Okay, we can go back. But basically all the stuff we're going through. So, what's the task? We want to find a conserved motif in an input set of these 3 sequences. And the motif, we think we are all about establishing a motif of 4 nucleotides in this case. Okay? So, we do it in an exhaustive way. You're going to try each of those 4 motifs and start with one motif of 4. So how many are there in the sequence set? There are of course 2 motifs, ACTG in the first sequence and CTGA in the first sequence. You have 2 like that, TAGC and AGCG in sequence 2. And there are also 2 given no length of those input sequences. 3. So we're going to use those fragments. So basically what you see here, randomly say we have now picked this motif here, ACTJ, to try and can we extend on this and can we build that into a motif that might be conserved. Remember the last lecture we talked about try all possible motifs. Look at this in an exhaustive way. We're only using motifs that are in the sequences. This method falls in that class. So anyway, so we have this, and now what you're going to do is you look in one of the other sequences. In this case, you'll see that this is, and you check, you just describe it, align it is simple here. You just line them up under one another without gaps, and then you abstract the profile. Do you see that this profile makes sense for this sequence? The letters are there, just one per position, so you are all or nothing. So of course this is the count of the letters. Letter A, letter C here, letter T there, and letter G for this fragment. You see which sequences are added here. Our probe, TAGC is this one here. AGC is the second one here. This is the first one in this sequence, and that is the second one in that sequence, as you see. So we do this exhaustively. Check all the fragments throughout all the other sequences. And now you just look what the profile will be. And by the way, this is this information score that I had. You score each of those profiles. Just with the score I showed you here. Where is it? This one. Okay. And the idea is that the higher that score, the more conservation there is overall in the profile. So the best profile has the highest score. So there you go. This is a pretty conserved profile, as you can see. So that's quite good. So the score is 5.5, as you can see. Now, look what happens here. We have this. Now we make the profile. You see it happening here. A and T are these letters and so on. You do it faithfully for each of these profiles, consisting here of input from two sequence bits, two segments, and these are the information scores. What do? You just check. You pick the highest one. If there are more, the highest, you just pick. You do something high road or left road here or leftmost or whatever. You pick one. You're happy. You go on. So after you've picked the best one with information from these two sequences, you look at the third sequence. There are still 2 possibilities in the third sequence, CTG or TTGC. You add it to the pack here, you make the profile, you calculate which one is it. And now you're done. If this is your input set, you would take this one. And that's it. This is your motif. So how great is this method? Is it greedy or not? Why is it greedy? Say it again. Yeah, could be that another combination, if you look back, would score much higher than what you have here. This is just as we say in Dutch, you look at your nose is long, not further than that, quickly do something. That's here. You just pick at this stage. It might of course be that this one, take that one and go to the third sequence, would have led to a much better score. Fantastic, you should have done this. I could have been so stupid not to do it. This is not what the algorithm is. It takes the best, no turning for the lady. And you go to the third sequence. And if there are 20 sequences, you do this, you build this up over all these sequences. In order, what would have happened if you would have taken sequence 3 in this cycle first? Would that have led to another result, you think? I think so. Anyway, so you see there's a lot to criticize here if you want. What's the advantage? Hopefully you get a reasonable motif out of this, and it's fast. Okay? So that's one possibility. And these steps that I just sketched in this example, it's the recipe. Right. So now let's go to a more general probabilistic framework and go to methods that are not greedy, not so greedy. They reconsider things or have a more inclusive approach, if you like. So, this is the mathematical approach. We talk about a set of sequences you try to establish the motifs out of. That's one until Sn. And you know, a motif M will be denoted by Pij, that's just a profile. That's just a thing like this, right? Where is it? I don't know. J, I is the number of columns, and J is the number of letters, and the alphabet size we'll talk about here will be 4 for a while, because we use different time sequences as an example. Okay, so that's just a profile, and so here you see that I is, these are the 4 letters, and here you have the width, number of positions coming from a multiple line. And the idea is, of course, again, find a very good motif that best resembles or represents conservation or anything like in the same sequences. The best motif. Now, we'll do 2 methods. In some detail, at least mean, because that's an important one. You'll recognize a certain algorithm that you're implementing as we speak. Expectation maximization. So I'll sketch for this method another example of that learning strategy. Do things differently. Okay, so mean and the Gibbs example. So again, you know, they're constrained, these methods. You just all the time talk about, okay, let's try a motif of 10 long. Run that method, see what you get. If you want to find 11 long motifs, be your own guess, run it for n equals 11, and so on. So that is not sort of decided by the method what length motif will be optimal and so on. This is not what this method. That's your input. Okay. And so, but they use really a probabilistic framework. Okay, first one, mean. So the EM here is motif, expectation, maximization, and something else. I don't even know where is the abbreviation. Read the paper. Is it here? Look, is it here? Expectation. I think they forgot themselves. Not that it's real. It's just a nice word, mean, right? And then just find something. At least there is expectation, maximization. Basically, the assumptions are there are motifs, and the assumption in the example I will sketch here is there is one motif in each of the sequences. And the question is, which motif of certain lengths, let's say 10 for now, I'm thinking, should you take in each of these sequences to make for the most conservation? So basically we go, but I will get there as we get there. Now, again, the algorithm is expectation maximization. No, are you using that? How do you call it now, that algorithm you use? Because the iteratively part of that. We're in the good area, the good arena, the proper arena. So, so that's what we will do here. So there will be an E step, an expectation step, and a maximization step. The idea here is, I think there should be a picture later. Here it comes, okay? So basically this is, and of course, you know, here again, this is very reminiscent, I hope at least, to your, to the Bauer algorithm you're implementing at the moment. So basically, a few of the assumptions, mean motifs do not contain gaps. It's silly, you know, these programs are about very distant motifs. Of course, you need gaps, you know this from alignment. I've told you that many times in the report. So what could you do? What might you hope to happen? If you think there is a gap, you might hope that you run me one time for the motif, you get something, then you run it another time, walk the first motif, and hopefully you get something, that you get a sense of gaps when you get two motifs. A region in the sequence that you might hop over and call that. So that is what you can do. The procedure itself doesn't work with gaps. So it does all of this on an input set of sequences. So here's the idea. You have sequence, and the assumption we will take, as is sketched here, we want to find a collection of motifs happening just one time in each of the sequences, such that if you line these up, if you make a profile, you get the best conserved profile. So these motifs, you know, are optimally conserved. We use, as I said, expectation maximization. So basically, how are we going to describe each of these motifs in the sequences? By the start sites in the sequence, you know, the residue number, the amino acid number, where each of the motifs will start, right? And if you are running the algorithm for 10 long motifs, of course, the position where it stops is 10 letters in the sequence. Okay, so again, we use a simple profile mechanism. Here you go, where you see that these values hopefully are normalized. They should add up to 1.0 over each of the columns. I think they do that here, so that's quite good. And so, as said, we'll discuss just one occurrence per sequence. Now, we all know this about the profile drive. It's the IMD model is there, it's mostly there in alignment. And, we'll go to use it. And once again, PIJ is just the profile. One thing that you maybe not have seen so far is, Blast is not using this, but these methods do this typically. A method region you're all about, you want to recognize what's called the foreground. So what is the foreground in this picture again? The foreground are the black spots in the sequences. So the regions in each of the sequences where there is no motif we call the background. Okay? And what do? We use information about that background. We don't use very much information. We describe the background just as one vector stating the expected or the observed whatever, frequency of the amino acids in the remaining positions of the sequence not being in a motif. But that is used in recognizing motifs. So you just suppose you set off the non-motif sites versus the motif sites. And that is what is said here. This is a bit mathematical description. That's a two-component finite mixture model, because you have the realization of the background versus foreground. So, how do we calculate those kind of things? For example, how could we describe, and what is going to happen is, we will describe, if there is a motif, certain given motif, 10 letters, in the sequence, to describe the chance, or the probability that that motif would start at a given position in that sequence. So here is what you see happening. This is the example. We have, is there a sequence given? So, we have a sequence of, I think, of 5 long. Yeah, here's the example. Just, 3 sequences, each of length 5. The letters don't matter now. And we want to find a motif with 3. The first question to you is, at how many, if you have a sequence of 5 long, how many sites would you start a motif with 3? Can you start at the beginning of the 5 long sequence? Yes. Can you start at position 2 of the 5 long sequence and have 3 letters? Still possible. What about position 3? Still possible. What about position 4? The motif sticks out by 1 letter. There's no problem we want. The button or head against the end of the sequence, so we should not do this. So that is why for a motif of 3 long, sequence of 5, you only need to take note of these frequencies, of these probabilities for the first 3 positions of each of the sequences. So these are the probabilities that a given motif, given profile will start at such a position, and what you see if you look is that the probabilities, there is a chance, because we said there should be 1 motif in the sequence. That is why the probabilities here add up to 1 for each of the sequences. You see? Now, what is this formula telling you? If you say, if you want to start, you don't know anything, you have not built these numbers yet, what could you do? You could start by saying, okay, I don't know anything. Let's say, the probabilities for each start site should be equal. So they should be, in this example, 130. So they will be divided by that length would equal 0.33 for each position. As a prior. Could be done. Okay. This looks horribly complicated, don't you think? In fact, it's I'm not allowed to say this according to these rules. In fact, it's quite simple. So I should say, as you know, it's not so simple, but don't worry. That helps you better. Keep it better. But let me talk you through it. So, no, let's do it with an example again. It's much easier. Let me go back and let's see what you get. So here we have a profile. And I told you that the profile will have the foreground, really the start sites for the motifs. And below. And here is the background. So this is the a priori probability of each of the letters in background positions not being in a motif. And this is what you typically do if you don't know anything. Put them all to a chord. I want to help you very much, perhaps. Yeah. Okay, so what is the chance now we have this profile? And we would like to, for example, find the probability of the fragment TAT 3 long in this sequence. Given this profile, we're going to use this profile. So what do? See what happens. what are we looking at? Why are we, so these are the frequencies we use, so the idea is where is the motif, TAT in position 3 to 5, 3, 4 and 5, meaning position 1 and 2, what frequency should we use of the profile? The background frequency, see that happening? No background here, for the first letter in the sequence, for the A, background for the second letter, the G, now we get in the motif here, so with the T in the first position, an A in the second, and the T in the third, and these are frequencies, look at that, we have a zero problem here, so we know for the come of this probability, whatever we do, there's a zero, that's the end of it. Anyway, zero is here from the profile, for the first position being a T, the point 2 is this point 2, for the second position being an A in this sequence, and the third here, the letter T, is a point 3 in the third position. Then we're out of the motif region, but in the remaining sequence bit with GC, and you take the background probabilities. Now it's a bit out of sync, apologies. Clear? Now so far you're a person, right? Now you need to think like a computer. How do you do it? So basically what can you do? A computer will go through those, so what will it do? Basically it will say, let's take the second letter. No, let's take the first letter. So the computer will go down and says, are you in the motif region? Yes. Are you an A? The computer says no. You know, I'm on this region. Yeah? Computer says no. Are you a C? Computer says no. Are you a G? Computer says no again. Are you D? Computer says yes. It's not little England. A little bit. Anyway, so that's what you do if you're a computer. And you do the same for the background, you know. Are you an A? Yes. Okay, done, right? If you could decide as a computer to just go on anyway, if you have seen the letter. So that's what the computer does as well. You know, it's not so close. Look, what we get, sorry. I'm doing something wrong here, where am I? To this horribly complicated form. So this bit here is for the background frequency. So here you go. You have a background letter, you're not in the motif region. So what do? For each of those probabilities, as you can see here, you need to go over all the background frequencies, take the product over all the positions of all these probabilities. You do this for the background, here you go, times, and you do this for the motif region. This is for the background, so over all those positions that are not foreground, you check, and what is this thing doing? Look here. This is called the identifier indicator. Yeah. So that indicates if you are the letter, are you an A? No. Then this thing will evaluate as 0. And this is a power function. Who knows what 3 to the power 0? How does that evaluate? What is it? By definition, right? 1. That's really good. And what is if you are to the power 1? What have you done? So you just have that number that's there, right? 0.5 to the power 1 is just 0.5. Really? So that's what we use. So this is that stupid thing. Are you an A? No. Okay. What happens? Becomes 0. 1. Are you a T? No. Oh, times 1. Are you a C? Yes. Times whatever is there. So this is just what this horribly complicated looking formula does. By this indicator, just ask the question, what are you? So this is what we do as persons here. I see it's a T. I take that number. Computers have to go through the list. That's what this formula does. Mathematicians also like this approach. So that's basically what you do. So this is how we're going to calculate the probability in these sequences, how we use a profile to calculate the probability. And this, by the way, will be part of the algorithm that will do this trick to find, in fact, the probabilities of star signs of a motif. Because this gives you a score for the probability that this profile describes, well, the probability of the TAT motif starting then at position 3. Alright, so here is the sketch. You've seen that. So what have we got? We have a profile that we need to build. And we want to even select that profile. That's what we want to train and to optimize. What have we got? That is the known bit. We have these numbers. What is the unknown bit? The hidden bit is, given these numbers, where the hell in the sequence would be the best position to start that motif. That is described by this profile. How is that done? Mean, that's a choice of the makers of mean. They check the probability that such a motif would start at any of the positions until the end. These are the probabilities that are normalized to add to 1. And then this distribution is used to find the best motif. So the chance is distributed. It's not, this seems to say it's that exact size, but mean is doing it in a fuzzy way. All these probabilities of any start site, this is really good, this is reasonable, this is not so good, is used to get to a final idea of what the best motif is. All that is taken. And that is used by this Z matrix that indicates the probabilities for the profile, the motif if you like, described by the profile, to start with them in the positions. So this one is a really good one. And normally you would say, okay, that's my arrow here, that's the position, but it also uses these probabilities. Okay? So basically, expectation, this is one thing, from this you get that, and vice versa, that's this arrow, it's the same thing, this corresponds. So you have the maximization step from these probabilities where the motifs start. We need to build the profile. If we have a profile, we can use the profile to estimate these probabilities. And the idea is that if you get a better profile, you get a better description of these probabilities, when you become happy, when you iterate it, like you become very happy now. I'm sure you do in carrying out this training protocol, seeing how we learn, so all that stuff. Okay, so what's the E step? That is, how can we use the profile to calculate these size? We just did it, right? That's this. Good stuff. I just showed you. So that can be done easily. There's just one difference, is that instead of just calculating those chances, we normalize those chances over the whole window length, of all the positions in the sequence. We want to say all these probabilities should scale to 1, right? With sequence, all probability starts at should add to 1, then you have to normalize. That's it. That's the only extension of what I told you before. So basically, this is calculating the motif start site probabilities if you have a profile. With all the numbers, of course, filled in, so all the numbers, all the frequency numbers. Okay? That example I just did a moment ago. This is another one now. This is for, what is this? Here, two ones are there to show you that there are different ones. So what is the probability that the motif begins with a T at position at position 1? What do you get? So this one, sorry, AGT at position 1 is here. What is the probability of that, having AGT as the motif? You just faithfully fill in these values again. Yeah. The Nobel Prize winner once said, bioinformatics is research that covers bookkeeping until real art. I don't know where you read it. I think I'm talking about some bookkeeping here again, but it's we do art with it, right? It's here. So, and if you want to find out, the motif GTA from position 2, then you would have, you would fill in, this would be background, you fill in the these letters, and again, you see, you shift from position 1 to position 2, and you would normalize it. Because again, the Z row probability should add up to these ones. That was the E step, the expectation step, using these start site probabilities. This looks again, you should worry, this looks also a bit complicated, but it's basically how do we build a profile when we have these, the probabilities of these start sites, of where the motif starts, where the profile would start in the sequence. Again, we have the realization that there are quite a lot of positions that will be background positions, where the motif doesn't land, and the foreground where the motif will land in any of these sequences. So, if you just count over all positions that are not foreground, that is this, then you have the background. Yeah. And here, this is the formula that is maybe more interesting for now, is how you build the frequencies, the profile probabilities, the values in the profile, in the motif regions. Again, I think I will have an example for this. Here you go. We want to build a profile. And the question is now, we want to build a profile of a motif of length 3. So how many columns will our profile have? Background. How many positions do we describe? If we have a motif of three positions, 1, 2, 3. What do we have? We do need the background. So we have 1 position more, 4 columns, right? 3 of which will describe. Anyway, this is how you describe the motif regions. And the idea here is, if we want to build a profile in 4x3, or 4x4 in this case, 4 letters of course, then the question is, what would the value in the profile be for the letter A in position 1 of the profile? The first motif. And what do you see here? And that is, the idea is then that that motif region would start with the letter A. Where in your input sequence set do you see the possibility of having a motif of 3 long starting with the letter A? What about, where do you see an A? Shall we name the first A that we see? I put in a suggestion as then A. The first letter in the first sequence. Could that be part of a motif of 3 long? I think so. Could you name that motif? I'll do it for you. ATG, how's that? Now my more difficult question. Do you see another letter A in that first sequence? The answer should be yes. This letter here, right? Could that letter be part? Could that letter be the first position? The answer is no. Again, if it's too far to the right, you would stick out by 2 positions. Not going to. Okay? So is there any other letter that might be used then as the first letter in a motif of 3 long in the first position? The answer is yes. And I suggest to you there are 2 more possibilities, namely the first A in the third sequence. So you would have motif ACH. And what about this A? Would that be? Yes, you would have motif AGT, also 3. See what happens here. So what do you take? You take these probabilities, the one for this A, the one for that A, and the one for that A. These are these 3. Yeah? First one in the first sequence, the first one is sequence 3, and the third one in sequence 3. You normalize it by taking, normalizing by the addition, the sum of all of these numbers in this probabilistic sequence. Yeah? So that is how you get to the first A in the profile. So where are we talking? That profile is a while ago, and I'll show it. Where are we? Where was there was one? Sorry, what did we do so far? No. Where are we? There was a profile, I've seen it. With the point through it. Yes, this one, sorry, I skipped. So we're on about, basically what did we fill in? Let's say this letter, right? We now have the value for the A in this position. We do that for each of the positions in the profile. We want to fill the profile, we want to learn from these probabilities of the start side, so to speak, yeah? Distributed delta sequence, and then we want to learn the profile. And when we have a new profile, we have a prior probability, then we get a posterior probability, and we go in iteration like you do for ASA learning. So, where were we? Here. So, how would you do if you would like a motif with the letter 2 in the second position? Where in the sequence could you go? Which z-scores would you take? It's not a z-score in the sense of so, tell me, I want to hear somebody. The second position in a motif below being a T. Do you see a possibility? Let me tell you, I see one possibility. Do you see one possibility? Which letter is it? Go that slowly, you say this one, that one. It would be a nice one, right? But it's not the second position, it will be the first. So, what about this guy? That could be the second. So that would mean you would only take what? The Z, this is the sequence Z guy, Z12 value. You would take this value there. So this is how you fill each and every frequency probability in your or non-use. Yeah? Not everybody's happy here, it's okay. It's not yet Friday with all the demonstration. Anticipation of that, you're not so happy here. That's okay. Anyway, let's talk about mountains then. You are running a very similar approach. Yeah, but now it's not about mountain tips, it's about valleys. Because that problem is harder. Think about to see the top of a mountain is maybe easier to stand somewhere in the landscape than the depth of a valley, because you know, it could be very much hidden behind the mountain. Anyway, As always, this is a very nice approach, but it will converge very rapidly. So where do you start? What is your first profile? What values do you stick in? Or what information is very important? And as is the case with your Van Welsh algorithm, it is a good idea to start in various places in this landscape to be able to hear. If the only trick you can do is walk down to the deepest valley, if you start here, this would be the best one. But if you're at this side of the mountain, you can only come. So to start at a number of positions in such a landscape will optimize the chance that you indeed end up in the global view. Okay, so that's this trick of me. So once again, I go back to the central notion. We have this iterative procedure. We want to learn a profile, and we learn the profile from the starts, the probabilities of the start side that the motif would start at any of these positions in each of the sequences, under the assumption that we just want one motif in each of the sequences. And then you iterate like this, so you learn these probabilities from the profile from these probabilities. But then again, to learn these probabilities, you can only get those probabilities in the profile. And that gives you the full flavor of iteration, where you have prior probabilities that are used to get an informed new set of probabilities. You have posterior, and then the posterior probability of iteration I will be the prior for iteration I as well, as you're doing at the moment. Okay? Mean. Now, that's one. That was a bit, maybe a bit tough, but now there's another guise of that. That was called the Gibbs sampler. Chip Morris, great man. We ended with this. This is the most unfinalized paper I've ever seen in the journal Science, I must say. Nice try, but it was just not finished when he had it. But he got it in, that's good. You know, American Journal, American Citizen, I don't know, something. But I'll talk you through this method. It's a sort of fast-track way of doing mean. So again, we have these, we don't have really these distributions. Here we say, we don't do a distribution, we want the best position where the motif starts. So this method has the notion, in each of the sequences, there is a best position where the profile will start. We only talk like that. That's maybe the main difference. So I'll give you the flavor, here we go. What's the trick? Again, now it's really the picture. So this method really only talks about the best position for the profile to start in any of the input sequences. But here, it's iterating in a bit different way. It closes the eyes, pick a random sequence. That's the blue arrow here. That sequence has been picked randomly, okay? Now, we start with some profile. You're filling it with priors, all equal numbers, who cares? You know, do something that you can start. So, we select that sequence. That sequence will now not be used. The blue sequence will not be used. What do? We use this profile. We slide this profile over each of the remaining sequences, all the non-blue sequences. Then we find that best position. It might be here in this sequence and there in that sequence. Yeah. And if we do that, we do the update step, we build a new profile. Given all of these positions in the other sequences, we now know what letters we have here, what letters we have there, and we can build a new profile. Now we say, okay, that's great. Then what do we do? We use this profile to slide over the sequence to find the best position. Now if this one new, the new position, it was blue, maybe now the best hit given the updated profile is here. Fine, we select, eyes closed once again, we select the new sequence. Maybe the bottom one, we do the same. We use the remaining sequences, update the profile, slide that profile over the sequence, and finally that selected or unselected sequence, if you like, the position again. Update the position, go. So one by one you update the position where the profile would start in each of the sequences, and while you do this, the profile is changing, and the idea is this should lead to this profile. Well, it's not a greedy method, but you could say it goes all over the place. But typically it converges pretty rapidly. So this is just a shortcut of mean, a little bit simpler statistics. Well, is it simple? Here are the statistics. But now you're not shocked, right? You know what this means. This computer again asking, are you a C? Are you a T? Filling the right one. Over the width of the mean. And what it's doing here, it's doing one thing different. It says, you know what? I want motif regions that are really different from the background. So it normalizes the score of the motif regions with the score of the background. The positions in each of the sequences where the profile is not landed, okay? That's basically how they score. And they use this score in this tool. Okay? Little shortcut of the mean method. And this was Chip Lawrence who had it in Science, as I said, in 1993. Now we're all a bit more proficient. These things that would fly, say 20 years ago, they don't fly anymore. Sometimes you start something, you pioneer, and then you sell the idea, and people like it, you get published. And then you try to do the same thing 30 years later, and people will laugh at you. This is old school, not true anymore. So there is the power of ID is also connected to the time of death. I give an example. A long time ago, there was a company called Burroughs. They were IT, they made computers. They came with a concept. There was memory, and I've been calculating with a computer that could hold 600,000 symbols in memory. It was big. So, but then Burroughs came and he said, you know what, it's all tedious, we create something that's like reading a book, You don't need to look at all the pages in a book, because you can turn pages, you read pages one by one. So you don't need to store the whole book in memory, just page by page, and you load the next page. That is called virtual system. It makes a lot of sense, we all read books, we do it now. But then people were arguing, and Burroughs came with that idea, and we looked at it and said, virtual is not real, right? There's something wrong here. Then also, big companies, IBM, no, they don't have it. Ooh, forget about it. So it was a brilliant idea. All architectures of computers nowadays have it. Business as usual. It's all virtual system with working memory, loading stuff. Just paging and so on. All computers do that. Burroughs came the first one. 10 years later, IBM just said it in advance. Slaughtered this little company and thought, now it's time to sell this idea. It's ours. It's over. Years later they came, System 370, really a good idea, please talk about it. You know that, then we find out what it's doing. And also IBM has launched good ideas, future system, it's costing its late 70s, early 80s of the last century, $4 billion, which was a lot of money then for IBM. You can say that. I think, oof, you can only use one time. That has been used, but really these machines have not been built. So anyway, it was just like a general promise. So all ideas of time. So Gibbs Adler. So the idea is it's like expectation maximization. It's only a little bit less well defined. That's why I think it's my surprise about this. The fact that they had it in science. It's a bit less dependent on the initial parameters. Is that an advantage or a disadvantage? So we get to you. It's certainly more dependent on the sequence really having the motifs and the position, and it searches less systematically through the. So the landscape is searched in a less systematic way. So it might have been the pitch of the mean authors, something would be the method. So this is what we did over last lecture in this hour. We've done this. With these probabilistic methods. So we've got exhaustive and greedy methods, the clustering method, and then these last two methods I explained to you. The Gibbs sample, as it's called. Okay? I think that concludes. Are we done with the hour? Is there early coffee? Where are we? Coffee. Okay, so now for something completely different. Not motifs anymore, larger ensembles. Now we're going to think about ways to find out about the evolutionary position of sequences, and of course again, what you can learn from it, what kind of positions the sequences might have greater importance than others, but also in what family would a sequence resort to, and that can help you understand the likely function, all of those kinds of dilemmas you might have. So this will be this hour, and then at least the first hour of the next lecture. I think the next lecture. Let's start it now. The evolution of logic. I don't know how many times I've done this past year, but probably at least once earlier on. Blavatsky, maybe I told you that I think if you carry a name like this, you have to become a scientist. No other way. So that's great. It's a very important geneticist, and he said this. And I sometimes paraphrase this, that nothing. Oh, this is a paraphrase here. This is what Blavatsky said, and this is what you might say is a bioinformatician or a seismologist, but that is close enough. Yes, we do a lot of computation. Yes, we do bound wells. We do all of this. We program it. We might like it. We might not like it. In the end, of course, we do this to learn something in living systems. Okay, so how does phylogeny come into play here? Well, phylogenetics is basically the study of the evolutionary history, origin of living organisms. And you know what importance these questions have, because I told you about morphology and homology and those kind of things, which you can well take from an understanding of the evolutionary descendants. So basically, ever since Darwin, you see these things. If you make a depiction, a representation of heritage, of descendants in evolution, very often you see these tree-like figures. Biologists, of course, made it, but that is what you still see. The way to represent those lineages is by means of producing trees, evolutionary trees. And then the branching patterns represent evolution divergence. And you've already seen a couple of trees in your current master program. Here is one. This is the tree of life. And you see basically that there are three main branches, if you would agree. And they're named the bacteria, eukaryotics, eukarya, Greek, multiple, and then there is a group, archaea. Now, a while ago, it was all very, very simple. There were prokaryotic cells, and there were eukaryotic cells, and that was it. And that happened all the way, from the first day of evolution, all until the year of 1977, when a heretic came to the fore and said, you know what? I've seen a group here, and I've discovered that you can do something with 16S RNA sequences. I've made evolutionary trees, and you know what? There is a third group. So, dear biologists, your landscape of prokaryotes versus eukaryotes needs to be made a bit more complicated, because when he gave that name already by himself, there is a sort of in-between group, and that we call archaea bacteria, original archaea. Yeah. What do you think happened? The guy had rough lives ever since. He was an idiot and a heretic. Somebody was talking out of any side, not his front side, and so on. So it was terrible. He suffered, this guy. There were papers about him, ridiculing him, even in science. So that was what you got maybe at the break. Good idea to become a type of seed. Little did he know. He thought he was innocent. He was not, according to the pack. Anyway, and it's really a funny story, because the firm thing was prokaryotes, eukaryotes. This guy consensus is the third group. So then people were, they were angry. They were livid. And now, when you talk to biologists and you say, what about prokaryotes? Again, they're totally angry at you. Because then in the meantime, they got used to the three groups. So you should not refer to the times when there were only two groups. So there is no prokaryotes versus eukaryotes anymore. These are the times of bacteria, archaea. And the old name can then still be the eukaryotic cells. So you get, it's always the same. When the view building, the main building, I'm sure you all love it. Yeah? The architectural style is not for nothing called, what is it again? Brutalism. That's the style. In England they call this style brutalism. Concrete, rough shapes. So it was an outcry when the thing was built. The whole event, this is a shame. Okay, you built such an ugly thing. So after all those years, the Freeport even got so, okay, yeah, maybe it is an ugly building. You know what? Shall we tear it down? Oh, That was 20, 30 years ago. Now whole after I'm up in the arms again, no, this landmark, you should keep it in place. Scandalous involuntary. So anyway, that's how people are. Also here. So now they used to get mad when you go back to the old times. They slaughtered Carl Lewis while he's still alive, and he got some prizes later on, but he had a rough ride. Threats, of course, the early to really have death threats, but he was treated in a unpleasant way by his peers. Not good. Anyway, but still, this third group is interesting. Here you see a few things. The fun about this are crazy organisms, you know, where nobody else can live. So boiling places down in the ocean, you know, where it's over 100 degrees, you know, we would be able to live there. Most of, you know, organisms on this planet. Archaea, they like it. And that's a very safe place to be. If you can live there, you know, you have no competition, right? Nobody else can stand it. So that's quite good. So because they are sort of extremophiles, generally, they live very often in extreme environments, although I must admit, we know more nowadays. There was, of course, the story early on, and now we find out, ooh, you also have normal archaea. So it's not the case anymore that they all live in these extreme environments. That was the early idea. But anyway, there's something to learn. Protein stability. What's dangerous in terms of fever? I think we discussed that. 41 degrees. What about 42? What about 43? I tell you, you're dead. Why? 100. They have proteins. They live at 100 degrees. So what kind of proteins are these? Very helpful lessons for building washing powder and so on. You know, they need more stability. It was at 40 degrees, or maybe even at 60 degrees with proteins. Anyway, so they do their special things, and they have that are like. So basically, go back again to the branch effect. What you see is the idea now is that the eukaryotes came out of the archaea. So this split is interesting. So it's not that the split started here, it's an early split, maybe between those, then this long branch here grew out, perhaps of the archaea, because the archaea are sort of taking a middle position. And here you see a few things. So, if you have them, if you have an infection, I don't know, maybe I don't know about really dangerous infection with archaea bacteria. Anyway, antibiotics won't help you if you have one. They help against bacterial infections, if you're lucky. You're not resistant. But certainly not against archaea. They don't have these branched, these straight sugars in their cell wall, which bacteria have. But then they have branched carbon chains, or complicated structures as well, and that is something that only the archaea have known to bacteria. And bacteria should have written here, and eukaryotes. I'll adapt it. So unlike the other two parties, okay? Right. So still, they're most similar to bacteria. We're still called prokaryotes, so don't lose whether there's a biologist in the room, a real one, an old one. I tried it once, got away with it. Believed, so as I said, the eukaryotes evolved from the archaea. That is because both have messenger RNA sequence. They have the similar polymerases, and importantly, archaea have introns as well. They do splicing, bacteria do not. It's a strong signal that there is a tighter relationship between archaea and eukaryotes. Okay, the idea is that archaea is still like a bacteria, that the cell is a big bag, there's no cell nucleus. So the idea is that from an archaeal situation, what infolding, what's the word I'm going to say? Infolding, yeah. So you have a cell membrane. Here is a cell. Now something happens, infolding, you get something like this. Could happen, right? Then the next step, you get sort of that it closes more and more. After a while, you might go to this situation. Infolding. Because the cell nucleus, the cell wall, has roughly the same material as this. So that's an indication that something like this might happen. Creating more developed cell organization. Okay? So, anyway, that happened a while ago, 1.7 billion years ago. Is the estimate. Okay. So, here you see what they can do. They can stand a hell of a lot of salt. We're there in Israel. there, this ocean there, where other organisms are not. They can produce methane, so they live in cows, and so on. And they can also live at very extreme temperatures. So they're funny lots. Anyway, this is about evolution. This is the landscape. These are the organisms. This is the variability. These are the three main kingdoms with all of their differences. From that, that's a substrate we should really learn from this with the phylogenetic methods we have. And I'll sketch those in this hour and the next lecture following this agenda. So first on what kind of evolutionary things can we see. Part of that will be a repeat. Some of you might have heard that before, but it's so important that I think it's not bad to run it past you quickly once again. Then we go, so we do a few methods. You do a few methods later on, but you are going to cluster together. Yeah, so that's what we do today. And then the next lecture, we will probably go on. Okay, so Darwinian evolution. You have a common ancestor, and now you get species that, like the archaea and so on, and you know, who will be derived from a common ancestor. And so, what do you need? The template. You should know those four things, right? Okay. And as you know by now, you know that nucleotide substitutions might change. So if you have a protein coding gene, the protein changes based on that mutation from not silent to non-silent. This is one thing in evolution that you find out that some species evolve at far more mutation rates, far faster, more rapid mutation rates than others. And you know, easily a 1,000-fold difference in mutation rates are there. So some organisms you know, develop, if you like, in evolution sense, 1,000 times faster than others. Where are we, do you think? Are we very fast? Compared to bacteria, what do we do? Are we slow or are we fast? What do you think? Compared to an elephant, are we slow or are we fast? And why would you say? Yeah. What do you know about an elephant in this regard? Pregnancy, how long is that in an elephant? 2 years. These guys are slow. Anyway, so it's probably slower. It's also a much bigger organism. Does it really have more cells, you think, than we? Silly questions. The answer would be no. What would that mean? The cells are bigger. Heard it already. That's great. So I think the answer will somewhere be in between. Yes, between more cells, but not like twice as heavy, twice as big. Larger structures. Anyway, and of course in Darwin we have the central idea of purified selection, the idea of the mutation that will be accepted by selection during evolution is only a small minority happening. Okay, so you've seen this essential non-essential genes, right? This is about fitness. Okay. Donna, did I show you this here? Have you seen this picture ever? I'm not sure. I want to look at that because I did it earlier. No, you will presently surprised. So I'll do it. Okay, good. K-A-K-S ratio. If you want to have a handle on how is that with selection? What can we do? And this comes in very nicely. It was there slided before. Yeah. So you have these essential and non-essential sites, right? So some mutations at the DNA level make another protein, and others won't do that. So we call those sites, KS are the sites where you have synonymous, the S from synonymous, mutations that do not matter when it comes to the protein. Okay? That's synonymous, right? And then you have the non-synonymous, which we might say asynonymous, so this may be where the A comes from, I don't know, it's English. These are the sites where you have the non-synonymous substitutions that do matter when it comes to building the protein, right? They change the protein. And then again, that might make a difference. The protein is not working anymore, or is doing something better, or it might not matter, right? It is not given also at the protein level. So this ratio, what will that tell us? The ratio between mutations that do matter versus that do not matter. What is Darwin telling us? Which pool is larger? Mutations happen very seldomly. Very seldomly, they matter So Darwin would think most will be, KA is normally bad news. You change something, we're conservative lot, we don't like. So most mutations, if they have it, should be synonymous according to Darwin. So you get a small ratio when Darwin gets his way. Yeah? So basically, what can you now do? You can look at those things, you make a multiple alignment of orthologous sequences, that's the best, really using related sequences, then you look through those positions, what is conserved, and which sites are, if you know them, are synonymous sites, and which sites are non-synonymous, you can count and calculate that ratio. Okay? Now, if you do this, here you see a few possibilities. For example, if you are a lysine, you can either use your codons, there are two codons, AAA or AAG, third position, and for aspartic acid, the letter D, single letter, you are either AAT or C. Now, depending on, of course, on base frequencies of these letters, you have to sort of estimate the chance that a K will go into a D. For example, what happens if you have far more C than T, then you would over-predict this one, but it doesn't matter. This is an example of a synonymous substitution, right? Because you do not change the amino acid. You need to cross from A to T, or from G to C, and so on there. So, some methods do a sort of correction to keep track of that things. But here you've got an example figure. This is if we compare a mouse genome against a rat genome. And this is the Ka-Ks ratio. Where is Darwin? Where is Darwin, please? I'll talk you through. This is the score on Ka-Ks. So this is 0.05. That means that Ks is 20 times larger than Ka, obviously. And but what do you see? Maybe you can't see it, but it becomes smaller and smaller. But even here, it's non-zero. The size between rat and mouse tissues. So what does that mean? That there are also sites where that almost, where Ka is almost as high as Ks. What does that mean? Darwin, please. So you can call that almost positive selection. With this selection on sites, those sites want to change the protein. Who knows a disease, a viral disease? The ability to change is very important for the disease to go on. 3 letters, we pronounce it as a word in Dutch. The only country that does that. What is that? HIV, what do we say in Dutch? HIV. Crazy. Anyway, nobody understands that. HIV. To be in an F, let's take the Dutch as well. We don't want it in a bundle park, but in a bundle park, as you know, that's, But anyway, let's keep bioinformatics. Oops, sorry. So, but that disease, right? How does that work? Why? Who can tell me if AIDS suffers or undergoes positive selection or negative selection? I'll talk you through. I do it in a simple layman's view of it, right? AIDS is a virus, and what does a virus want? It wants to duplicate in an organism and then go to the next organism. So the whole world should, these viruses are a bit, narcissistic, I think. That's the idea. Grow and be big, spread out the whole world. That's kind of easy with some people. But they seem to want to do that. So also AIDS, but what do they need to fight? That's the human immune system. And that immune system takes roughly 24 hours to build up recognition. So the virus comes in, the system says, ooh, something odd is going on here, what is this? It builds up, this is a bad guy. It then makes the weaponry to kill that bad guy. And they look at the head of AIDS, and they recognize the head AIDS. And AIDS think, you know what, if I manage to change my head within 24 hours, the recognition is built up for the guy I love anymore. So that's the idea. So the immune system tries to build up recognition. After a day, it says, nah, I'm changed. The immune system, bloody hell, and you think, oh, there's a new thing here, let's go after that one then. 24 hours later, right? And so what is happening? The immune system is totally busy trying to not, it's not doing anything else anymore, and that's what gives you the symptoms. But what is the idea? That the functionality, the virus can only survive because of positive selection. No Darwin here. I need to change. If I don't change, I'm wrong. So there's a whole many changing proteins, and of course in those places where the system will stay intact and so on. But that's 8. So here, what we would expect. If we talk about Darwin says, oh, no, non-modifications are bad news. They bring the system off, but don't do it. So Darwin is category 1. Certainly smaller than 1 is the ratio. Then we have the other side. This is H, positive selection. You need to change your proteins. So you need non-mutations more, so the number goes up. And again, the elephant in the room again, as I told you about before, Kimura says all this stuff is important. Evolution is neutral, it doesn't matter. And if you adhere to that idea, then of course you would expect this ratio to hover around. Okay? So that's just a bit of extra information that phylogenists, evolutionists try and squeeze out all kinds of information by looking at alignments, basically, in all different possible ways. Right, this picture you've seen, you need to know this. Just memorize. Remind you, right? Okay, and this you might know as well. This is, what is orthology? That is if you have a common origin. How can you observe that? Very difficult. The common origin normally is extinct. So we need an operational definition. Here you have one. Okay? One is widely used, but there are quite a number of methods to establish a definition. You recognize your most likely gene in the other genome and vice versa. That sort of reasoning can be done in different ways. And there are a whole series of methods for making use of such an inclination, such a field, such a definition. Okay, phenology, just to remind you, is there too. Horizontal transference, sometimes also called, right? The story of being in the elevator, being changed when you come out. That's this. Now we go to clustering, I promise you. So, this is general science. You go do something, you measure something. Very many times, very many different fields, not only life sciences. You resort to, you study a number of objects. Here we have 5 objects. And then we measure a number of things about each of those objects. How high they are, how sturdy they are, whatever you want to measure, what color they have. And typically, you represent all that information in a table. A table with columns and with rows. Rows representing the objects, and the columns representing, in this case, the characters. The features, it's now called also, right? But then you call characters, not features. Anyway, if you look at this from a sort of a mathematical point of view, what have we got here? The idea is if you have 5 objects, 5 cows here, and this is length, and this is liters milk per day, and so on, and all kinds of things you could measure about a cow. Then you have here a mathematical situation where you have 5 objects floating in space of 6 dimensions. Right? I can't depict 6 dimensions to you, but I can do 3 here. This is what I try to do here. So the idea is you have a bunch of 5, a cloud of 5 points, sort of being positioned somewhere in the 6-dimensional space. And the idea is, would it be nice to be able to discern blocks, dots here that are closer together, might be defined as a unity or something that's made together and so on. So the notion of being close in that 6-dimensional space. If you want to do this, then there is a whole suite of methods, and I will not do too much because in the January course, even the next course for you, where you all will go, we'll talk about this as well, and a bit on the take. So I'll give you the sketch more what will happen, and then you go into hard cracking stuff. In that course. So again, we have a table, and it's a 2-step rocket once again, just like last, but in another way. First, what are we going to do? We have here, let's say we are in the Netherlands now, right? And we want to position the cities. Groningen, Maastricht, Amsterdam. What do? You make a map, right? What's the definition of a map? How would you describe the coordinates of a Dutch town? I think 2 numbers will do. Do you agree? X and Y coordinates. If you're in Switzerland, you might want the Z coordinate, but this could be certainly right? It's as flat as a pancake. So the data set will be a 2-dimensional, a whole series of dots, or city names, and the table would just have 2 features, the X and the Y. So basically that's this table, right? Here are a few more dimensions. Now what do we do here? From that table, from these towns and these coordinates, x and y coordinates, we can maybe calculate the distance between each of those towns. You can do this in various ways, right? So if you've done that, then you can construct a table with the distance between Groningen and Maastricht, and so on, north and south of this country, and so on, and have that. If you have a fully described table of the distances, some people say, then if you have that, then you can build back the exact map. Do you agree? You have all the distances between the 6 main towns in the Netherlands. Can you build back the map? Give me a few. I say one word to you, mirror. Can you build that map? Can you discern a mirror image in terms of distances from the mirror? And the answer is no. But if you would know just one thing, like Arnhem is to the east of Utrecht, you've solved this, right? So you don't need to know a lot to really have the full map. But I'm telling you this because in fact we are throwing away information. In this table, the exact position in the map is lost, you only have the distances, right? But that way of representing your data helps because that is used, and there's a whole, army of methods that can do clustering, and we'll run through a few of those in the remainder of this lecture. Okay, before we go into all this technology, the question why should I bother is always of some importance. This is what you can say you want to learn, right? Maybe, I will talk about cows a bit more, but suppose you want to buy cows for a cheap price on the market that give a lot of milk per day. How could you see that? Maybe the stripiness pattern of the cow, the farmer should know this who sells the animal. If you know if there is a spot there and there, then it gives a lot of milk. Who would create a cow? You tell anyone. So it comes to do it. You say, oh, this looks very ugly, these spots. This looks good. That's the price down, and so on. So, finding a topology, finding relationships between data points and features is very important. So all of this basically is pattern recognition, so you try and discern all kinds of trends in your data. That's very important. Yeah? Okay. Now we have let's do a few things with the table. You can do quite a few things with that. This is just let's say we have a data set of 5 cows again. We measure the height in millimeters, and we do the size of the legs in kilometers. We do that, right? It's total freedom. But then I would argue the column in millimeters will show far larger numbers than the column in kilometers where you measure sizes of cows, right? So you might want to normalize that table so that, for example, all columns would fall in between 0 and 1. And if you want to do that, then there are 2 ways of doing that. The easiest way is you look up the largest number in each of the columns and divide each of the numbers in the column by the max. If your column is only has the numbers 1 and 2, how will that work out? So number 2 will go to 1, the number 1 therefore will go to half. That means that you don't have that the lowest number is necessarily 0. If you want the lowest number, if you want the highest number on 1 and the lowest number on 0, then you do it. You look at the minimal number and the maximum number. You use a simple formula, check it, so that is 1 and 2 if you only have those. And you will see that 1 will evaluate to 0, and the number 2 to 1. So that's a way to normalize a table, because that is required if you want to do cluster analysis. Now, this is the first step. We want to convert the towns in the Netherlands, the 2 axes, the table, to a set of distances or similarity numbers, the opposite side of the same coin, similarity numbers. So here we have distances, and you see here that Minkowski, another great name in science, also Polish by the way, had a set of, this is a definition of distance, and you see there is a letter R, so this is the power R, and then you take the root of the R. Again here, you might recognize, if you learn in school, Pythagoras. Do you remember Pythagoras? C squared equals, that again? A squared plus B squared, so C equals the square root out of A squared plus B squared, right? That's this. Square root if R is 2. Here you've got city block distance, right? So, but R could be 3 and 4, and then you get other metrics to calculate the distance. So how does this work out? I told you it would be all about counts. Here we go. So, we have two counts. They have a length, a height, and a width. Here, these are the scores, whatever metric, doesn't matter. It's probably not kilometers or whatever. Not meters either, I don't know what metric it is. But these are the numbers, okay? And so, how do you calculate now the distance between cow1 and cow2? Now this, if you go to Euclidean, this is Pythagoras basically, it's now over 3 features. You take the difference, 7 is difference of 4, 7, 4 difference of 3, 3, 5 difference of this is positive, so this should be negative. But if you fill that into this formula, it wonderfully goes down to 5.93 square root. So that's the distance where you use R equals 2 in Minkowski metrics and Euclidean distance. If you do city block distance, this is the definition. You just take the absolute value of the differences, add them up, and what do you see? These two cows float in space in exactly the same spot, but depending on the distance criterion, you will get the difference. Okay? That's the first step. That is to convert, or here, to convert a table of these cow numbers to a set of distances. All pairwise distances. Here we have that, then we prepare for the next step, and that is from here to a dendrogram, and we'll do that step as well. So the ones that I will cover are here, single linkage we'll do today, complete linkage we'll do today, group averaging we'll do a little bit today, and these ones we'll do in the next lecture. Okay. What should I tell you? If I give you a cucumber, and I give you a sharp knife, and I ask you, would you like to cut the thinnest possible piece of that cucumber? So, a matter of death and life, right? If it's not thin enough, then you'll suffer dearly, right? So you're a bit nervous, you move, you will cut my fingers, sharp knife. So you're looking, tearing your eyes because you look at a very thin slice of fact. They say, make life easy. Why don't you rephrase your problem? You know what? You take the knife and you try and just cut as thick as possible slice. How's that? Then you take the other end. You have the same thing. And maybe it's psychologically or otherwise. No, it's not that. So you can formulate your problems in different ways. And that's here as well. Basically, we try and find, these type of things. We have, this is a dendrogram. So basically, if we have a cloud of points, we want to put in groups, you could say, you know what, I'm going to say, view this like a pack of loose points, and I say, oh, I first put these two together, and then I put that together, and then I put this together, and then in the end you have the organization. Or you do the other way around. You say, I view them as one cloud, and I will start chopping up. Here I cut them into groups, and I will put that group into. So you have agglomerative clustering, taking things together, starting with loose points, taking them together, or the visit methods, that is taking the knife, cut a group in two, and do that repetitiously, so that you get also maybe a dendrogram. So what does a dendrogram show you? Basically, it's a protocol where on this side you have 5 loose points. This is dendrogram with 5 objects, 5 loose points. It's not so interesting. And at this side here, it's not so interesting either because you have one cluster, one group of 5 points. All the bits are not interesting. The interesting bits are in between, right? Here, for example, you have 3 groups. Here you have 2 groups. Maybe that's interesting. So on the way in the dendrogram, it's almost a trajectory showing you how these groups are interrelated. Yeah? And then one other thing, in my early days, I saw papers in Nature and so on, where they said, this is really very surprising because it turns out that whatever the salamander is very close to human. Here, look, here is a human, there's a salamander. Is that correct? Or is it? Why not? Show you here. This is a dendrogram. Basically, it's like a mobile in the baby room. You hang it up, you take it on the tip, you hang it down the ceiling, and you can rotate everything. Meaning, distance between objects is only in this direction. This doesn't matter anything because I can turn this one so this one could flip to the top side. So this organization doesn't mean a thing. It's really, so the distance between this object and this object is all the way until here and back again. That's the real distance. So this is the distance. This is just a placeholder to be able to write a nice tree. These lines do not have information about the distance, the vertical lines. Okay? So, this is what I told you. Basically, you move from a non-interesting situation of 5 loose points to a non-interesting single cloud of points, and the interesting stuff is somewhere in the middle. Alright. What can we all measure about sequences and use? Well, here is a list of things, the composition of the nucleotide, if it's DNA or amino acid composition. We talk about protein sequences. You might want to measure the isoelectric point or molecular weight, and all kinds of things. You could use the cluster subdivided groups, but you know by now, I hope in this course, if you want to learn about evolution, you really need to do sequence alignment, so you know about the letters in the sequence. Okay, and why is that important? Well, ever since Darwin, we do the comparative analysis. You learn by comparing. Of course, phylogeny and alignment is one of the most important means of using comparative science. Okay. Well, here you have a few things where phylogeny can be used. Knowing about the tree, you can use trees. We've discussed that, by the way. You know, to discern between morphology and paralogy, predicting secondary structure. You can use phylogeny a lot. Host-parasite relationships. You have receptor molecules and binding molecules. So in a lot of fields you can use phylogeny to learn. Yeah? Okay, now let's do the full thing. First step then, this is, you see what happened? We have another input now. That's how I do see, this is how it works. So what do we do normally? You've seen this already in multiple alignment. You have a set of sequences. You create all against all distances. By alignment, pairwise alignment, and then you do the clustering criteria. So in this lecture, I will explain how this could be done. And I promised you that before to do that, so I should give it. Here's just an example how it works. The two-step rocket, this is an input set of sequences. We convert that by whatever distance criterion to a matrix with pairwise distances. You can see that this matrix is symmetrical, meaning the distance between A and B is taken to be the same between B and A. And here is the dendrogram, comes out of the program. I'll explain these red numbers later on. And now the biology starts. What do you think? Is this a good tree? You're a biologist, right? Whatever you know about it. You know these names? You remember that guy, yeah? Here, you know that one, I think. This is all sort of animals. And what's all this stuff when you see this? It's the smaller stuff. This is big bacteria, right? But who's eaten yogurt in his or her life? You know this word. That's it. Yogurt. So what's the evolutionary story here? We've made a tree. I'll tell you a story, you know. This is this bifido, the yogurt wants to become humanized. They're climbing. It's like, you know, they say, you know, I don't want to be bacteria anymore, you see. I'm much better. I want to, you know, belong to the higher pack. And it's like all these whales you find every now and then, they come onto the beach, right? What do people tend to do when they see them? Or beaches, throw them back. And this whale says, but I want to evolve too, you know. I want to become a land animal. Oh, but that is so nice. Anyway, it's kind of a joke, right? So you have that here. And so bifido's trying to become better, and you know, these people eating yogurt and things, it's a terrible situation to be in. Anyway, basically, from a tree, you can generate very interesting stories. And now another thing, suppose this tree will be completely wrong. Then you get even nicer stories. This is the fake news area also here, right? You make an incorrect tree, you get the craziest evolutionary stories. Very interesting. A lie is normally more interesting than the truth. Not in the case of the American president, but you know. Okay, so here we go. We'll do the first two clustering methods, and I'll give you a feel how that might work. and then I stop. Okay, we've done that. Here we go. We have a cloud of points. We do Euclidean distance, meaning the distance is just a straight line from one dot or to another, right? So tell me, what is the nearest distance here? What would your first merger, your first cluster of two objects be? Which one? This one? Are you happy? Good. You get yeah. All right. But now we have to make something. We need to tell how we go on. Because what have we got now? We have a number of loose points. Now we have one cluster now with two elements in it. How should we define now the distance between the cluster and this point? Now, this method is called nearest neighbor. Have you got an ID? And the simple definition is here. If there is a cluster, then a point outside that cluster has as a defined distance between that point and the cluster, the distance between the point and the nearest point. So that means the distance from this point to the cluster is the distance from this point to that point, the nearest point. Okay? That's how it works. So, given that situation, what is the next step? What's now the nearest point, you think? I'll do it. Yeah? Even if you don't agree with this. We go on. What's the next step? Given that clustering definition, single linkage or same nearest neighbor. That one. I go on now. And that one. And that one. And that one. Then I'm done. Yeah. Okay. So, go back and see what happens. Is this a strange way of clustering? What kind of dendrogram would be the result? How would that look? Do it once again. What happens all the time? We add one point to a cluster that is in place. You see that? So how would the dendrogram look? Like that. And what do you think? How great is this? You want to analyze your data set. This is your, have you got a good sense of grouping? This is the cow family A, striping ones, not giving milk. These are, giving milk. You can't do so much, right? So here again, you have the standoff between mathematicians and biologists, because mathematicians will tell you this is the only method that is mathematically correct. And then a biologist says, yes, for us it's the only method that never gives us any information. There you go. That's life again. So, let's do something else then. Let's reverse. We go to the same data set, but we do an opposite method in a sense, and that is now not called nearest neighbor, but furthest neighbor. But what's now the definition? The distance between, who can guess that? The distance between this point and the cluster is not the distance to the nearest point, but to the furthest point. So the larger distance in this case. So, do the clustering for me, given that scenario. What's the next step? Now that, different, same data set, different clustering method. So I do a few things. This is how I do cluster. We're done. Okay? I go back so you can see it one more time. Okay, what datagram will be the result of this? This one, same data set. Have we got now a better sense of grouping? I think so. Okay, so these are more structured clusters. Same data set, same distance criteria, Euclidean, but a different clustering criteria. Gives you another result, okay? So if you want the algorithm to do this for single linkage, then we're done and you can do the rest yourself because I see you're all not going to your practical. Yeah. Okay, so here are the distances measured between each of the objects, right? So what is the simple algorithm? What is the first thing you did? You did this in the picture. You take where you start. What's the first thing? You take the 2 points that are closest. What are the 2 closest points? I suggested by red. It's B and D at a distance of 4. Correct? So here you go. B and D will be taken at a distance of 4. You see that here? What's now the next step? What should we now recalculate? We take those two together. So our matrix is going to shrink. We have group A still, point A, we now have cluster BD, and we have point C still. We have now a 3 by 3 matrix. How is this distance coming about? Why is this 5? Who can tell me that? Why is the distance between the point A and the cluster BD 5 under the nearest neighbor assumption? Why is that? If you know that, then you understand. Okay, what do? You evaluate the distance from A to B. What is that? Can you look it up? It's here, 5. And the distance from A to D. What is that? 9. What's the smallest? 5 or 9 is 5. You put 5 in, right? You go on, do the same thing. What's the smallest? It's the 5. So you take that one, you see that coming, and the last step is here. The distance between C and this cluster ABD. Check the 3 distances, the smallest is 6, and this is your remaining determinant. You see what happens? It's changing again. Now we do the same thing. You check it at home. This is the same data set. It's now with complete linkage. The furthest distance you take, here you go. What is now the distance? And you get this answer. Okay, I think I'll leave it at here and go on the next one. What's wrapping up? Yeah.